Hello. In this video, we're going to be looking at how we can apply the conservation of energy for the inclined plane, which is a good example of the advantage of using energy versus, say, forces. So, if you're trying to deal with the inclined plane using forces, it's a bit messy because forces and acceleration are vectors, and because the motion's at an angle, you end up having to rotate your coordinate systems and things like that. It can be a little tricky, but if you can get away with using energy, it's very nice because it's a scalar quantity. You don't need to worry about coordinates and the like. And the reason why energy is so important in physics is it's a conserved quantity. The total energy of a system is always constant no matter what. Or you may hear it as energy can't be created or destroyed, only transferred from one form or system to another. And the way that we'll apply this for an object on an inclined plane is if we solve for the total energy at one location, that's the same total energy at all locations. And you use that to see how energy is distributed at different points. The downside for energy is friction can be a little tricky to deal with. And if there is friction, you typically have to fall back to forces and Newton's laws. So let's look at our conservation of energy. In mechanics, our total energy is kinetic plus potential energy plus heat if there's friction present. And the sum of your total energy, some of those forms of energy has to be a constant. And it's the same constant no matter when or where you're looking at it. Kinetic energy has a nice definition. It's 1/2 mass times speed squared. It's just a flat value like that. The potential energy is based on what forces are present in the system. And when you're dealing with the inclined plane, the potential energy you have is due to gravity, which is the mass times g times the relative height of the object. And so the height here for the potential energy is always in reference to some location. So you could say that at h equals 0 corresponds to the bottom of the incline. And as for heat, it's something that you only have to worry about when there's friction, and you look at how heat flows or heat builds up over time. You can always set your initial value to heat to be 0. If you do have to deal with it, heat is also the work due to friction, and that would be the force of friction times the length of the path. So let's look at our problem. We have a block of mass m. It's sliding down some incline that has a certain length, has a certain height, and has a certain angle of inclination. And what we'll do for this case is look at what's going on at the top versus what's going on at the bottom. So we'll start at the top. And at the top, it may be at rest, it may have some initial velocity, we don't know, but that kinetic energy is just 1/2 its mass times its initial speed squared. And if it's at rest, the initial kinetic energy would be 0. And it turns out for the potential energy, all you care about is the height. You don't really need the length or the angle of inclination unless those are the only pieces given. All that really matters is the vertical distance for that potential energy, and initially you can always set your initial heat flow to be 0. And so at the top, at the start of our when we're observing the system, the total energy being kinetic plus potential plus heat would just be 1/2 the mass times that initial speed squared plus that potential energy mgh. Then what we'll do is look at what that energy is doing at the bottom. So at the bottom, the object is now moving at a different speed, so we'll have 1/2 the mass times whatever that final speed is squared. And since we're at the bottom, the height above ground is 0, so there's no potential energy. And unless we knew something about the force of friction, we don't have a good way of solving for the heat right now. However, what you can do is use the total energy from the top of the incline and look at how that energy gets distributed at the bottom, because the total energy is constant, and in mechanics it's going to be equal to the kinetic energy plus potential energy plus the heat. So we solve for the total energy at the top. That was 1/2 the mass times the initial speed squared plus the potential energy at the top, mgh. And at the bottom we have the kinetic energy at the bottom, 1/2 the mass times the final speed squared. Potential energy is 0 since we're at no height above the ground, and we've had some heat flow due to friction. And so we can rearrange that to get that heat flow due to friction, which would be the potential energy at the top minus kinetic energies, or more precisely 1/2 the mass final speed squared minus the initial speed squared. So why would we do this, and what are some of the consequences here? When you're dealing with energy, it's more about what's going on at different locations versus what's going on at different times. So unless, say, you're looking at the power, the rate of energy is transferred over time, time really isn't going to factor into any of your equations. Additionally, when you look at this equation for the heat flow, the angle of inclination doesn't really matter. All that matters is the relative height of the object. And so if we want to find the heat, we need to know the change in height, the initial speed, and the final speed. If we are missing one of those pieces of information, we have to go back to dealing with forces and Newton's laws. But where it gets to be really powerful is when there's no friction or no heat flow. In which case, if there's no heat flow, we can solve for the speed at the bottom based on the speed at the top and the height at the top. And so we don't have to resort to the kinematics equations for the velocity and position in terms of time. We can solve for the speed at the bottom just based on the height and the initial speed. And again, that's without resorting to any of the tricky business with rotating coordinates. But again, if there is friction, it can get a little trickier. But let's say we don't know the final velocity and there is friction. What do? We have to resort back to Newton's laws and the force treatment for the inclined plane, where you have to deal with rotated coordinate systems and all that business. And I have a video on this treatment, how you deal with forces on the inclined plane. And I'll put a link in the description. But this is what you would do. You would basically solve for the force of friction, and the heat flow from friction would equal the work done by friction. And the force of friction in this case, when there's nothing else pushing on it, would be a coefficient of kinetic friction times mg times cosine of theta. And the work done by friction, which would also be the heat flow, would be that force dotted into the path it took, which would be the length of the incline. And it turns out, because you have the length times cosine theta, those can be condensed into just the x distance, the horizontal distance. But this is how you would deal with the inclined plane with energy. And again, its power is when there's no heat flow, but you can still deal with a problem when there is heat flow.